evening and welcome to the Bath Royal Literary and Scientific Institution. This is the Geography and Adventure program, and we're going to welcome tonight a distinguished speaker, Professor Danielle Schreve. Professor Schreve is the head of the Department of Geography, the Centre for Quaternary Research at Royal Holloway College, University of London, and is particularly interested and involved in the fossil mammal records from 2.6 million years ago, and has a particular interest in biostratigraphy, which is the fossil assemblages used as dating tools, and the reconstruction of past environments. Obviously, that includes climate issues. But I think very interestingly for us who have assembled here to learn something extra about the paleontological record is that Professor Schreve is particularly interested in cultural enrichment and in public engagement. So I will now hand over to Professor Schreve. Thank you very much.
Thank you. Right, good evening everybody. It's an absolute pleasure to be here. Thank you so much for coming out. And I think one of the things that I want to bring across to you is that I will be talking about something that is almost on your doorstep, but also bringing together aspects of geography, conservation biology and climate change as well. And although I won't be talking very much about early humans, it's important to appreciate that what I'm going to be talking about will be very much a backdrop to human evolution and dispersal in Britain. So we're going to start off by introducing you to the Quaternary. Now, when I say that I'm a Quaternary scientist, a lot of people are puzzled by the word Quaternary. And I think if there's one mission that I have tonight, it is to tell everybody that the Quaternary is important to us all because we are in it now. It's the geological period that we are in today. And in fact, it goes back to 2.6 million years. And as you can see with this climatic record, so climate curve, it is drawn from the deep ocean. So this has been achieved by drilling down through deep sea sediments and extracting a climatic record. You can see that as we come through from 2.6 million years towards the present day on the left-hand side of the graph, that for most of the time, we have actually been in the blue part of the graph. We have been going into or coming out of relatively cold climate conditions. But that really takes off from about 1 million years ago. So if you look at that point onwards, you can see that there are then huge swings into very deep and pervasive ice ages, roughly every 100,000 years. So these are punctuated by periods of warmer conditions. These are referred to as interglacials, and they are of relatively short duration. So a few last 15, perhaps a little longer in terms of 15,000 years, but many of them last about 10,000 years or even shorter. And in fact, we've already had our 10,000 years of warmth. So actually looking back at these warm stages is important because they offer a good natural baseline for understanding the duration or the intensity of warm stages in the past. And that will be particularly important as we move into a warmer world with additional temperature increase, but also, for example, seasonality of rainfall. So these things give us an opportunity to look back in time. So overall, you can see that this is an enormously dramatic period of time. There's a lot of climate change going on, and at the same time, this is also the backdrop to human evolution, but also the evolution of the fauna, which we're going to be talking about tonight. So what we're going to do is actually zoom in to look a bit more closely. This is the last wiggly graph that I will show, I think, almost. So we're going to zoom in a little bit closer to look at the structure of the last cold stage, because although I've been interested in looking at warm stages in the past, what's occupying me now is the question of responses by animals to very abrupt climate change right at the end of the last ice age. And the climate curve this time is drawn from the Greenland ice cap. So this is devised from drilling down into the ice and again extracting a proxy paleoclimate record. So you can see that where I've put the orange arrow, this is the point of the last interglacial, the last warm stage before the one that we're in now. It was a period of relative warmth. It was a time when Britain was occupied by hippos, rhinos, elephants. Doesn't mean it was like Africa. These were species that were completely normal, native to Britain at the time. But summer temperatures were a little warmer than today, perhaps 3 degrees warmer centigrade. And then you can see really from about 100,000 years, and we've got our time frame at the bottom, you can see that we move into the last ice age. And as we move through that, you can see that it isn't uniformly cold. Far from it. In fact, it's a really climatically dynamic period, which is punctuated by cold stadials, periods of cold climate conditions of short duration, and warmer interstadials. These are brief periods of warmth. And there's roughly a 16 degrees centigrade change between them, and those transitions can happen in a matter of 100 years, a couple of 100 years, sometimes 1,000 years or so. It's really, really rapid. And as we come through time, eventually by about 11,500 years, you'll see the abrupt, rapid warming up into the current interglacial, the Holocene period. So the time period that I'm going to be talking about is this extent here, over the middle part of the last ice age, from about 50,000 years until the start of the Holocene. And one of the big questions for me, as a paleontologist is how species respond to these really abrupt climate changes. Do they move, adapt, or die out? It's a time when a lot of the megafauna is coming under a lot of ecological stress. We see mass extinctions happening in various species. And one of the things that faunas are doing at this time is seemingly reorganizing themselves very, very rapidly. So this is an interesting question because for a long time, we have struggled with the concept of what we call disharmonious faunas. I always find this a weird expression because we describe something as disharmonious, comprising of species that today do not live together. We describe them as disharmonious because they look different to today. But actually, movement was the thing in the past. Communities would break apart and species would move at their own pace in different directions and come together in novel situations. One of the things that we have struggled with is actually, for example, finding good sites where there are long records and undisturbed records that we can do radiocarbon dating on, and to really examine whether these disharmonious faunas are real or whether they're just an artifact of poor preservation, inadequate dating, for example, are actually things mixed together and we're not seeing a true picture. So this is one of the things that we have been trying to achieve. Right, we're not moving on for some reason. No. We're stuck. Oh, there we go. Right, we're moving again. So I love this quote. This is a quote by the journalist George Monbiot from his book Feral, and it's all about the technique that I use in order to interpret the past. And he says, paleoecology feels like a portal through which you may pass into an enchanted kingdom. So very lucky, we will be going into the enchanted kingdom tonight. And really the paleoecology, the name is very self-explanatory. It is the ecology of the past. Modern ecologists today deal with observations and measurements in years, decades, sometimes even hundreds of years. But of course, paleoecology allows you to take that longer time perspective. We can go back thousands of years, sometimes tens or even hundreds of thousands of years. And that allows us to make much more balanced judgments about how fauna has responded in the past. So particularly looking at these questions of where species are naturally distributed today, for example. We can see that many species today are threatened, endangered, they are in refugial areas. And we often mistakenly think that they must have retreated to a core area where conditions are most suitable for them while they're threatened. And in fact, that may not be the case at all. For example, things like Scottish wildcat, they were distributed all over Britain in the past. And actually, the Highlands of Scotland may be a marginal, unsuitable environment for them. So actually, if we look further back in the record, we can see where they would normally be distributed under natural circumstances, and perhaps think more creatively about the types of conservation decisions that we're making. And paleoecology allows you to do that. So I'm going to take you just to the south here, to the Mendip Hills in Somerset, and you can see we're just to the south of Bristol in the National Nature Reserve of Ebor Gorge. So it's owned by the National Trust and managed as a National Nature Reserve by Natural England. So this is a limestone gorge. It's composed of Carboniferous Clifton Down limestone, and it's an area that's full of caves, very well known for its caves. And our little cave is up on the flank of the gorge, but there are many other caves that are known from this gorge, and obviously locally as well. The small caves that are found elsewhere in the gorge tend to contain later prehistoric or Romano-British material, so only a few thousand years old. But of course, just down the road, we have got the famous site of Wookey Hole, so famous for its antiquarian collections and fantastic collections of Ice Age material. And I'm delighted that here in the room tonight, we've got fantastic collections from the Bath Royal that include material from Wookey Hole. So these are 19th century antiquarian collections, and there's an array of material from woolly mammoths through to giant deer. There's lion in there, hyena, bison, there's a bit of horse in there as well. So some fantastic material, and I'll be able to give you a context for that material as we go through the talk. So when I was first taken to this site, this was back in 2006, so we've been digging at this site for a long time. And it was found, reported several decades previously, because of a tree that had blown down in front of the entrance to the cave, but it had never been excavated. And you can see that the entrance was relatively modest size, so it was about 1 metre wide and barely much higher. And it leads up through a gully in the limestone to the plateau at the top. And it's unusual to find a cave that hasn't been excavated, because of course in this area, many of the caves were excavated by Victorian antiquarians and others subsequently. So to find something that is completely pristine is obviously unusual and also a very special circumstance. So we had no idea what would be in this. We had to pick our way along the side of the hillside because there was a very, very steep slope going all the way down to the bottom of the gorge. And I crawled into that cave on my belly. The limestone roof was above my head, and I really couldn't see very much except a bit of discarded badger bedding, some hazelnuts and a bit of dirt. But being pioneering souls, we thought, well, we'll give it a go. And we came back to put our first trenches in the following summer. And this is what the situation was like a little bit later. So this is 4 years later. And in fact, the original entrance is just at the top right. So you can see that part of the entrance. We dug down into this reddish deposit that you can see built up on the right-hand side. This is a limestone breccia, so it essentially means broken up limestone. And depending on prevailing climatic conditions, it's alternately bound with clays or silts during warmer climate periods where you've got soil holding vegetation together on the landscape, but sometimes during periods of cold climate, the sediments are really loose and really there's nothing binding them together. So actually the sediments themselves are telling us a story about climate change in the past. We put our first trench in, and on the basis of the samples that we took, we recovered remains of a tundra vole that had not been here since the end of the last ice age. So that was already very exciting because we knew we were onto something. And we continued, we came back and were able to enlarge the trench and then gradually work our way out towards the northern side of the cave. Now, originally when we started, we agreed with the National Trust archaeologist, who gives me my permit annually, that we would leave half of the cave undug. So this was important. It was intended as a repository for the future. And it was absolutely the right aspiration to have from the beginning. So as we went down, we left the sediment undug. Of course, it was very difficult to say what half of a thing of unknown dimension was, but I completely arbitrarily started to excavate on the northern side and said we'll leave the southern half. So we proceeded, and as we went on, of course, we got deeper and deeper, and we began to have to shore this section up. So the idea being that this would exist for the future, because of course, when I go into caves today that have been worked on by Victorian vicars, for example, the sediment has largely been removed. So unless there has been very detailed recording, which was not the case at the time, sometimes it's a bit like trying to interpret a jigsaw puzzle with half the pieces thrown away. So it was the right thing to try to preserve the sediment. But you can see there that we've identified the sort of margins of the cave opening, and we're going down. We're about 4 meters down at the time. And this is what the sediments look like inside. So they actually are quite horizontally bedded. So there's not a dramatic slope on them. At this point in the sequence, most of the sediments are coming down that gully from the plateau and simply tumbling into the cave. So they've built up over time, and then eventually they are capped off by a flowstone or stalagmitic floor. So you can see that with the white crust that is there, and in fact you can trace it all the way around the back there. So the sediments are actually quite easy to dig. You can trowel those reddish sediments, but as they get close to the cave walls or underneath a drip line, for example, they become impregnated with carbonate-rich water from the cave formation process. And there you can see those white deposits. Those are cemented, they're like concreted onto the side, and we have to drill into those. Sometimes you can see bones exposed within them. So that's the sequence. We were very fortunate that the cave appeared to infill and was then capped off. That flowstone is not continuous, it's broken up in places, but pretty much nothing had disturbed it until the point where we began to excavate. So this is the way that we go about the process, and the cave is subdivided into grid squares. You can see next to one of my former students there that he's standing on the left-hand side. There's a vertical plumb line coming down. So we have a way of recording things spatially within these grid squares. But also when we find remains of anything larger really than about 2 centimeters, we record it in 3 dimensions using the total station, the electronic distance meter that you can see in the second shot along. And of course that's great because we're recording things in 3D, but a lot of the time when we're digging the sediment, even if you're really sharp-eyed, you cannot see remains of tiny voles, shrews, mice, lemmings, bats, all of these tiny things that our Victorian antiquarians largely ignored because, quite understandably, they were quite interested in collecting big things like woolly rhino teeth. But these are really important environmental indicators. So systematically, we now collect the sediment and we bring it back to the laboratory. We've excavated over 284 tons of material since 2006, so 252 inside the cave, and the remainder outside the cave. I'll talk a bit more about why we did that. And over 60 tons have now been processed, by which I mean they have been washed through a 0.5 millimeter sieve, dried, and then under a microscope, the tiny teeth and bones picked out. This is an incredibly time-consuming process, but it is worth it because of the fabulous nature of this record. So we've now got more than 4,000 large mammal and bird remains. Some of them are beautifully complete. Some of them are very fragmentary, just small pieces. And by the time we have finished, I'm confident we will have over 1 million microfaunal remains. And those are remains of small mammals, but also things like reptiles, amphibians, and we also have remains of fish in the cave as well. So interesting to speculate about what kind of predator might have brought these in. So in contrast to the sediments, which are coming in through different mechanisms, mostly tumbling down that gully and into the hole, the remains of the bones that we find are generally beautifully preserved. You can see some of them out here tonight. And they are remains of animals that were either living in the cave or which were brought in as prey. And one of the things that we do as we go through, as we expose the deposits, we also begin to reveal more of the actual shape of the cave as well. And so periodically we get the cave 3D laser scanned, and this is work that was done this summer by Tom Elliott from the University of Liverpool. So I'm just going to show a short bit of the fly through into the cave. It's not a huge cave, we're still going down, it doesn't go back very far, but nevertheless it is one of the most important archives of its kind anywhere in northwestern Europe, as we'll come on to see. So this is rather nice, being able to see the outline of the cave, but of course these are the limestone walls now, so the sediment has gone from this area. So recording what we do is absolutely critical, and making sure every 10 centimetres that we go down in a square, we are sampling material, and we are then taking that back to the lab to extract all the small remains, as well as the large things that we recover. So we've got, eventually the idea will be that we have the shell of the cave, and then within it, we will have all our 3D finds plotted, so that once the excavation is finished, we'll have that outline of the cave, and then all those remains plotted. We can look at the relationship between them. So what we're seeing here is, and unfortunately, we're just cut off the top part by the bar at the top. But you've actually got a climate wiggle going from old, about 17,000 years, up to about 10,000 years here. And this is a plot of the radiocarbon dates from the upper part of the sequence. So there is a climate wiggle, again from Greenland, superimposed at the top. That's the blue wiggle there. And you can see the dates are expressed as a range. So all radiocarbon dates have an error on them, and they are expressed as a calibrated date, BP, which means before present. And you can see that they cover from about 14,500 years, with the youngest ones at the top, things like wildcat and mountain hare, at about 10,000 years before the present day. By that point, the cave was completely infilled, and there was nothing else able to occupy that space. But the climate wiggle at the top shows us that we are coming out at this particular point of the coldest part of the last ice age, a period known as the last glacial maximum. We then experience a rapid warming about 14,500 years ago, and it looks as though we are coming out of the ice age into the current warm stage, the interglacial known as the Holocene. Things then go a bit wrong, because about 12 to 13,000 years ago, there is a period of climatic deterioration. This is a phase known as the Younger Dryas. The ice cap in Scotland expanded, the polar ice front in the North Atlantic came further to the south, and this is because of the breakup of the big ice sheets, particularly the Laurentide ice sheet in North America. It's discharging big pulses of cold water into the North Atlantic, so we have this sharp climatic reversal. And then, thank goodness, about 11,500 years ago, we warm up into the Holocene, the current interglacial. So these dates show that this part of the Gully Cave sequence exposes a pretty complete sequence actually through this very climatically complex period. Okay, we've stopped again, I think, every time we unmute. I'll try that again. Okay, there we go. Right, so the title at the top says the late glacial interstadial. So this period of abrupt warming where we think that everything is great, we're coming out of the last ice age. And you can see the dates, the radiocarbon dates there, so in calibrated years BP. And what I've done is just to show you the species that we have represented. And I've shown them in a very simple way by colouring them in red if they are species that we find in southern England today, in green if they are species that are present in Britain but not in the south. They generally occur from the Midlands up to Scotland, or in blue if they are cold climate exotic species. And you can see that there is a real mix in there. We've got everything from short-tailed field voles, common shrews, pygmy shrews, the kinds of things that we would find today, mixed in with tundra species such as narrow-skulled vole, northern vole, and collared lemming. Mountain hare, which today is our native British hare species, is also very abundant. Now, interestingly, in the larger mammals, we have red deer through this period, but wild horse is only present early on. The early part of this brief warming period is rather more open and much more suitable for wild horses. As soon as the trees begin to come in, so we know that there was the spread of birch woodland, that at that point then the horses seem to disappear and red deer persists. So there's a real mix. We've got some tundra elements in there, we've also got some woodland elements in there. What this does is to underline the fact that these disharmonious communities are real. These are securely dated, they are in stratigraphic order, they are underpinned with a robust chronology. But the climate is changing so rapidly at this time that we can't see any evidence for specific adaptation. Species are moving rapidly, and it's just too quick for any kind of adaptation to be taking place. They're shifting their range in response to this climatic warming. The other possibility, as I've mentioned here, is that we have micro-refugia locally. So this is interesting geographically, because if we think about the environment of the Mendips, it's characterised by these steep limestone gorges, where there could be more sheltered micro-habitats available at the bottom of those steep gorges, in contrast to the really open and pretty barren plateau that we find on Mendip. So those micro-refugia may have also allowed some of those more temperate adapted species to cling on in conditions that would otherwise perhaps be less good for them. We then move on through time to this period of climatic reversal. So this is the period where the Scottish ice cap is expanding. Of course, we never get glaciation down as far as the southwest, but nevertheless, at this particular time period, during the Younger Dryas, it then becomes extremely cold, savage cold conditions. At this point, the cave is an Arctic fox den. And I'm just going to dive across to show you a skull of an Arctic fox. So a beautiful little specimen. There's a complete individual that is found curled up in a niche at the back of the site, but other remains also found at the site as well. So we've got lots of crunched up bone in there. And you can see that as climate has deteriorated, so we get the increase in cold adapted species. And this time, things like Norway lemming, collared lemming, and a new addition of a steppe lemming, but still other tundra vole species. We have mountain hares still present. They're obviously tolerant of both cooler and warmer conditions, and a new addition of a steppe piker, which is a little relative of rabbits and hares. But yet, even at this coldest time period, we still have persistence in small numbers, but they're still there, of species that are characteristic of southern England today. Now, obviously, these small mammals are not living in the cave. They are brought in by birds of prey, which are hunting over the landscape, just as they would do today. And, for example, owls coming back to the cave, roosting, regurgitating pellets and the undigested parts, the teeth and bones, other things that fossilise. So some bias is possible in there. We might have, our owls might be favouring a certain type of prey, but we can be pretty sure that what they're picking up is an accurate reflection of what is around on the landscape at the time. At this period, we still have wild horse present, but also reindeer. So it's coherent with the picture of the cold climate event. Again, sort of tundra, boreal, steppic indicators based on habitat preferences, and often with cold periods, we begin to pick up evidence of aridity. So I've just shown, you can't quite see it with the top one, but I've just shown because I want to make a point about how quickly species are on the move. At this point, between about 12 and 13,000 years before present, we have these cold climate species that today are not sympatric. They do not live together, but yet they come together in decades to, a couple of hundred years to be living in the southwest of England. So at the top, we've got the steppe pika, this little relative of rabbits and hares. They have this habit of collecting vegetation, which they store over the winter. So these become quite common in our cave. And today they live in Central and Eastern Europe across to the western part of Central Asia. Below them, we've got the collared lemming, which has a circumpolar distribution today in the Palearctic. Beneath that, we've got the Norway lemming, which you can see has a Fennoscandian distribution, and then rare records of the Siberian steppe lemming, and you can see the distribution of that extending all the way into the eastern parts of Asia, and of course our Arctic fox here. So this really brings home the point about how quickly species can move if they have to. And again, we think today about what might be happening under climate change, how species may need to shift their range, how quickly that can happen, what we might need to do to facilitate that, to keep these species alive. And at this point, we also have an extraordinary appearance of a very unusual species occurring in the southwest of England. And this is the Saga Antelope. You can see a lovely illustration there. They are today extremely endangered. They are Central Asian species with populations occurring in Kazakhstan and Mongolia, for example. And yet, because this is a period of climatic deterioration, the spread of aridity makes these animals, gives them the ability to extend their range. And so they move out of Central Asia into Europe, and they also spread in the other direction towards Alaska. And you can see some remains actually from one of the caves in Cheddar Gorge. This is from Goff's cave. There's a tooth and also a heel bone on the right. So a really unusual species, but one that is really important as a climate indicator. And then finally, we're actually up into the Holocene. So again, the title is hidden, but the Holocene, the current interglacial. So things warm up rapidly from about 11,500 years ago, and we start to see a mass expansion of temperate adapted species shown in the red. So a lot of the things that we would find in southern England today. But we also get new elements coming in, and these are what we would describe as obligate thermophiles. So they have to have warm conditions, or arboreal species. They need the presence of trees. So things like common mole, they can't survive in seasonally frozen ground, so we don't find them in permafrost areas. So a good indication that we're now into a warm interglacial. But also hazel dormouse, again, another endangered species that we find in southern England today, and very reliant on trees for movement and obviously nesting as well. For a little while, those cold adapted species cling on, but eventually it just gets too warm for them. We have things like aurochs, the ancestor of our domestic cattle, coming in. These are typical warm forest-adapted species, and they come in bang on the warming of the Holocene. Things like reindeer cling on for a little while, but eventually it's too warm and too wooded for them to survive. So by that time, the cave is largely infilled and it's capped off. There's nothing that is infilling that cave anymore. But the interesting thing for me is that actually this period of the early Holocene, the early part of our interglacial, is just as disharmonious. The mix of species in there is just as extraordinary as what we found previously. So this has been a real eye-opener in terms of the research. There's also fabulous remains of birds there. We've got about 2,000 remains of birds. Caves are great places for the preservation of material, largely because they're calcareous, so it's good for preservation of bones and teeth, but also they are really good for the preservation of fragile bird bone material because they offer relatively sheltered, buffered environments. So I've just illustrated a small range of the species that we have, but we've got a lot of things like game birds. We've got things like red grouse, grey-legged partridge, black grouse. We have a number of predatory birds present, but clearly there could be other predators that were using that cave and we don't find their remains preserved. But we do find remains of kestrel, both adults and juvenile, so we know that they were nesting in the cave. Also long-eared owl. And one of the most common species throughout is the jackdaw. So there's lots of jackdaws in the gorge today. And we even have remains of, we can tell this was a female bird, and it's because it has a particular type of bone called medullary bone, which is laid down by female birds during the nesting season. So we assume that this female jackdaw died in spring. So fantastic level of resolution. And most exciting, we've also got remains of great bustard now. So again, this is a species that has been reintroduced on Salisbury Plain, but we now have evidence for it right at the end of the last ice age. So in terms of human evidence in this upper part of the cave, it's very circumstantial, if at all. We certainly have got no stone tools, so there's no direct evidence that humans were ever living in this cave. It's quite small at the time, so you know it might have been a useful stop-off point for shelter, but there's certainly there's no artifacts. But what we do find are articulated remains of large mammals. So actually at the top right, hopefully you can just about make out, it's actually the thigh bone. You can see the ball of the femur and then the main part of the bone shaft there. This is from an aurochs, but we also have the shin bone and the other bones of the leg that fit onto that. So there was a whole haunch of an aurochs in this cave. That's quite an unusual thing for a carnivore to bring in, and it's much more consistent with activity by humans. We also have a cluster in a discrete part of the cave of bones that show both impact fractures and also discoloration. Now, the impact fractures are important because you can see here with this deer humerus, so the upper arm bone from the forelimb, it's got a very sharp break at the top. And this is consistent with the bone being smashed and twisted to extract the bone marrow. Now, hyenas would do this routinely in the past, but hyenas are long gone from this time period. So, you know, we're looking at a time period about 14,500 years ago. But humans do this. So Neanderthals, modern humans, and indeed their forebears do this because bone marrow is incredibly nutritious. So it's got interesting impact fractures, which would be consistent with human exploitation, and also this odd discoloration. And there doesn't appear to be any kind of chemical reason. It's not manganese staining as far as we can tell. And it's consistent with bone that has been in proximity to a source of heat, but not burnt. When you burn a bone, it turns white and becomes calcined. This has just got this discrete sort of black flush over the surface. And so we've done various bone-related experiments. So you can see we've mocked up with some cave earth, made a little fire on top using species that were around during the late glacial, and buried bones with flesh, without flesh at different points below it. That fire gets incredibly hot. Within about 15 minutes, it was almost at 900 degrees. It was really burnt very, very hot. And you can produce discoloration on those bones with material that's about, say, 5 centimetres below the source of heat. We've never found a hearth in the cave, but there may have been a hearth outside once upon a time, which is no longer preserved there. And these could be bits of material that have got kicked or brought by carnivores into the cave afterwards. And we do find flecks of charcoal right the way through the sequence. So that's the first sort of 14,500 years up to the present day, but we were still going down. And as we dug down, the sediments got coarser and coarser. You can see there's some real big blocks appearing there. We dug for 2 years through about 2.5 meters of sediment across the cave and found almost nothing. Were it not for the fact that, you know, the sort of camaraderie of having the dig team there and sort of keeping everybody going and hoping there was going to be something coming up, I think we might have given up at this point. There were some interesting indications, though, that there might be something lower down. So actually there was a chunk of reworked speleothem, flowstone, which is deposited under more temperate climate conditions. And it had obviously been torn up from something below and reworked into these deposits. The only things we found were 2 bird bones, but they were interesting bird bones. One of them was from a long-tailed duck, and the other from an Arctic skua. So these are both very cold climate species today. They nest up on the rocky outcrops, the foreshores up in the Arctic. And it seemed that having gone through these sort of more temperate period of the late glacial interstadial, we were coming back into something colder. And that certainly was consistent with what we would expect from our knowledge of the climate curve, because between about 20 to 25,000 years ago, we're in the period of the last glacial maximum, the coldest point of the last ice age. There's almost nothing living in Britain at this time, and certainly nothing significant really in this particular cave. But every year we would dig, on the very last afternoon, we would dig a little pit, hoping that we would get down into something different, and that would give us a clue as to what we would find the following year. And so we were able to do that, and in 2015 we got back into finer grained deposits, and it turned out that it was a bear den. So a brown bear den. It was filled with bears, some of them aged individuals. You can see at the top right there is a really worn canine tooth. It's actually out on the table here, and most of that sort of black part is actually the root, and the tooth itself, the enamel part, is worn to a stub and exposes the pulp cavity. So this would have been a bear in considerable pain. So there's some older individuals that probably died during hibernation, and worse still, were then picked off by hyenas, possibly even killed during hibernation. And that's because if you look at these 2 images here, you can see that the edge of that bone has got a sort of scalloped edge to it. That's typical of hyenas, gnawing away at the edge of the bone, trying to get at the bone marrow. And there's 2 puncture pits indicated with the arrows that are consistent with the canine impressions as the incredible powerful jaws sink through the flesh and they make an impact on the surface of the bones. So we have remains of older bears, there's some sub-adults in there, but there's lots of juvenile milk teeth as well, so there were baby bears in there too. So that cave is being used as a place to rear young, and there's a few other bits and pieces in there as well. So a bit of extinct Ice Age bison, some reindeer, and also some Arctic fox as well, but it's mostly occupied by brown bears. Now, as we went through the brown bear level, we got onto these enormous boulders. So they were just, really difficult to break up. So we had to drill these and to take them out. And to my astonishment, below those boulders, we found a proliferation of bones, including some huge ones like that bison radius. It's a 4-limb bone that is on the table. That was right below one of those biggest rocks. So this was incredibly puzzling because the huge boulders had clearly come from that entrance, the upper entrance, collapsing. But if there was material below them, that entrance was not in existence. So how on earth had those bones got into the cave? So this was one of the things that we were trying to establish. There were all sorts of things in there, a massive amount of reindeer. You'll see one of the jaws down there, very large-bodied red deer, wild horses, more bits of bison. So lots of interesting things. And we had to think that there was some other way that the material had got in. At this point, it's clear that the cave is a hyena den. And that's because not only did we find remains of hyenas, and you can see top left, there's the back of a hyena jaw. So it's huge. Again, it's out on the table there. It's shown next to the largest hyena that I have in my modern comparative collection at Royal Holloway. So a substantial, really robust animal. We think of hyenas today because, of course, they're sub-Saharan African animals. But in the past, they were much more widespread. Their range has been curtailed by human activity. They were all over Africa, all over Europe and Asia. They were incredibly successful predators during both warm climates periods and also cold climates. And those hyenas are largely predating young, vulnerable individuals, particularly, for example, remains of wild horse. We've got remains of foals in there, but notably remains of reindeer. They're going after reindeer calves. And you can see with the jaw on the top right that we haven't refitted the bones on this jaw. So you can see where the white arrows indicate these are spindly little milk teeth with the adult teeth waiting to push up underneath. So this is an animal that's only a few months old when it was predated. This is the top of a baby reindeer skull. So you can see where the antler bases were. So it's mostly a hyena den. There's a lot of crunched up material in there, but we also found our first artifact at the site. It's only small, it's out there on the table, but it's a flint flake. It's absolutely characteristically struck by early human, and it bears all the traces of a humanly produced artifact. It's made on flint, which is not a local material. People would have had to have gone about 15 kilometres to the east to go and find flint, but it would have been a really important resource. Now, this cave was not occupied by people. You wouldn't have gone in it when it was full of hyenas or bears, but at some point, the large carnivores can't have been at home. Somebody came along, they presumably sat outside the entrance of the cave. And although the cave now is it's a great place to work, and when we've got the lights up, it's actually quite a cozy place as well. But if you think back to it being a hyena den, it was probably full of stinking, rotting carcasses, all sorts of horrible things. So somebody probably sat outside, they napped some flint, and a bit of flint pinged off over their shoulder and landed in the cave behind where we found it. So no great evidence for human occupation, but nevertheless, we know that people were around at the time. Based on the dating, I've just got some new radiocarbon dates back. I think that that artifact is probably made by a very early representative of modern humans, our species, rather than Neanderthals. So modern humans arrive in Britain about 40,000 years ago. So the mystery still went on about how the material had got into the cave. And as we went down, and actually because of the witness section that we maintained, it was getting rather tight in there. But we could see something that looked like a sort of alcove appearing at the bottom. And maybe this was a second lower entrance. But of course, most of the slope outside went up to the bottom of the lower entrance. And of course, we couldn't go from inside and burrow outside with meters of sediment above us. So we had to start taking the material down outside. So this is it's very coarse material. There's occasional reindeer remains in it, but nothing that is age diagnostic. And then eventually we had the breakthrough. So we were excavating down, and a hole appeared, and one of my colleagues climbed up into the entrance, went down the bottom and poked his hand up like a zombie coming out of the earth. So we knew that the connection was there. And then, of course, we're now starting to open up this new lower entrance. So when the hyenas were using this cave, that upper entrance didn't exist. This is the way that the hyenas went in and the way that they brought their prey in. We have no idea how big that feature is. It could be relatively small. We might find the floor of the cave quite soon, or it might be as big as the Dome of St. Paul's. We honestly don't know how much further down we will be going. It also explains why at this particular point there's a lot less sediment in the cave, because for the upper part of the cave, sediment could come down the gully and just fall in, whereas here it has to blow or be carried in horizontally. And one of the most beautiful finds is a baby woolly rhinoceros. So these are 4 associated milk teeth. This is from an animal that was about 2 years old when it was killed. Adult woolly rhinos were just too big and too powerful to be brought down by hyenas, but we know from other sites that the calves were more vulnerable and could be taken as prey. So this environment is a really rich one. It's one that's often referred to as the Mammoth steppe. And it really brings home the fact that this was a highly productive environment. Yes, we were in the middle of the last ice age. There were lots of climatic oscillations, but broadly speaking, we have a huge extinct ecosystem that extends all the way from Britain right the way through to pretty much to China. A rather arid environment. It's low precipitation, so there's not deep snow. That's great for things like woolly rhinos, which are quite stocky and don't like deep snow as far as we can tell. And from carcasses and bones that have been retrieved in Siberia, it's been calculated that the total herbivore biomass is about 10.5 tonnes per kilometre squared. Now, that's not far off what we see in the savannas of East Africa today. So it really brings it home that this was this really rich environment that's crisscrossed by huge herds of mammoths, woolly rhinos, reindeer, bison, wild horses, and associated predators like hyenas and lions, for example, and indeed Neanderthals and later modern humans following after them. We only find traces of this extinct ecosystem up in the far north of Siberia today, for example, on Wrangel Island. And there, the system is being driven by the activity of grazing herbivores. And we know this because we've got July temperatures of about 1 degree centigrade. The grass should not be growing and be beautifully green like that, but there is high animal nitrogen input, namely from reindeer, which are dunging all over the area, and the grazing activity also maintains the open aspect of it. So the large herbivores themselves are ecosystem engineers. They're driving this. And in fact, there's a rewilding experiment, the Pleistocene Park in Siberia, which is attempting to reproduce this kind of system using large herbivores as the drivers. But because it's relatively dry and open, we see a lot of species coming in that today again have more easterly European distributions. So things like European ground squirrel, today present in Bulgaria, Hungary, Slovakia, these open steppe-like grasslands, they move at this time into Britain, and we find their remains in the cave. So we know that this particular time period is a dynamic one. As we mentioned right at the start of the talk, this is the period that is characterized by these very rapid climate oscillations between cold stadials and warm, brief interstadials. And you can see these are more radiocarbon dates going from about 60,000 years towards 35,000 years on the right-hand side. And again, the Greenland climate record is at the top. So what we're seeing here are plots of woolly rhino dates for the last ice age. And you can see that by about 35,000 years before present, woolly rhinos go extinct in Britain. The last ones are from a site up in Scotland. Presumably they retreat from the south and they track their environment north and then eventually disappear. And we're heading after that period into the last glacial maximum. Maybe there was more precipitation, higher snow cover, things that woolly rhinos would have found hard to tolerate. Or it may well be that modern humans are hunting them to extinction. These animals would already be under ecological stress because of these climatic transitions. And perhaps just a little bit of extra hunting by our species would be enough to push them into extinction. And what we're looking at here is the record for collared lemmings. This is a fascinating study because it brings together DNA and climate change. And it's making the point that species do not stay in one place, and they're not sort of constant right the way through. This is a record that is drawn from sites, so it's a record that's drawn from sites both in Somerset but also from Belgium as well. And each one of those sort of grey points there indicates a different genetic clade of these little collared lemmings. And what's happening is when we radiocarbon date those lemmings, we can see that those genetic clades correspond with the coldest parts of the climate curves. So what happens is when the climate cools, a wave of lemmings comes in, probably from somewhere like the Ural Mountains. Climate warms up into one of these brief interstadials. The lemmings don't like that. They go locally extinct. Climate deteriorates again. A new wave of lemmings come in. So with this kind of resolution, we're actually starting to see population level turnover, which is an astonishing level of detail to observe. So having gone from starting out in Gully Cave, knowing that we were covering, say, the last 14,500 years, through that sort of brief warm period, then the climatic deterioration of the Younger Dryas, and then the warm up into the early part of the Holocene, we've now been able to extend the record back to about 45,000 years ago. So this is really astonishing because the cave preserves this wonderful archive of material. And for the first time, we're actually able to see how the fauna is changing over such a long time period. So the excavations continue. We've now got a rather more open area in the cave, and that's because eventually we had to remove that witness section. And that was entirely down to the nature of the deposits. The material at the top held together very well, the material at the bottom held together very well, but the stuff in the middle that dated to the last glacial maximum, the period when we only found the 2 cold climate birds, wasn't bound with sediment, and we could hear it slumping away inside the box. And eventually, of course, the fear was that the upper material, which we were trying to conserve, would eventually fall down and would be compromised. So in association with Natural England and the National Trust, we excavated it under the same controlled conditions. So you can see the outline of the cave inside. That's the situation from the most recent excavations, where we can see the lower entrance starting to enlarge. And obviously it's an amazing place to take students and to give them some training in this kind of work. I just want to finish by making the point that although the evidence of the ice age, the changing climates, the turnover in the mammals is fascinating in its own right, or at least I think so, there's also a message here for conservation. This is where we bring together conservation paleobiology. And that's what comes back to what I was saying at the beginning, that we need this deeper time perspective. So some of the things that we have been able to achieve through work at this particular site have been, for example, undertaking applying new techniques, using, for example, shape recognition on the teeth of these little voles, and actually discovering that a species that we do not recognize as native, the common vole, Microtus arvalis, and you can see it's with the map, we have the short-tailed field vole, Microtus agrestis, shown in pink, and that's the one that we have in Britain today. We only have the common vole as an introduced species on Orkney today, but we've been able to demonstrate that at the start of the Holocene, actually this species was present. This is a real native species, it's a new native, and therefore that has conservation implications for this species today. Similarly, of course, the type of material that we're subjecting to ancient DNA also gives us an insight into sources for wilding or rewilding. We're talking about bringing species back in, especially species that have real ecological value. As ecosystem engineers, for example, these might be things like Eurasian beavers for preventing flooding, or lynx for maintaining numbers of deer up in the Scottish Highlands. We're thinking about these things now. And actually, it's good practice to rewild with the closest relative that we had in the past. So actually knowledge of which species were around, what they were coexisting with, what prey base was around. If you just look back a little bit further into the past, we can get a much clearer picture of what things were like. And so that really comes down to that point about establishing natural species range, that many of the species that we consider endangered today are existing in marginal habitats, and they were more widespread in the past, and we should look at that. But also establishing these baselines for conservation, how warm was it, how open was it, all of these things that we need to consider. So that brings me to the end, and I want to say some thank yous to all of these lovely people who have supported us in many ways. So the dig is entirely funded through goodwill and charitable donations from various individuals and bodies. So as we leave the enchanted kingdom that paleoecology has given us an insight to, we can look across towards the tour at Glastonbury. And it's a view that people would have appreciated for millennia in the past. Obviously, thanks to my fabulous students and colleagues who also help, I could not have dug this cave on my own, and we're still going down and we'll be back there in the summer again. But also, thank you very much for inviting me to speak. Thank you for listening, and I'm very happy to answer any questions.
Just a bit of housekeeping at the moment. I would ask those who are online tonight We will take your questions via the chat function, so please use the chat function if you are viewing this lecture on Zoom, and we will try and take your questions in sequence. And perhaps there will be a few people in the room tonight who would like to lead with a question or two for Professor Schreve. Thank you.
Yes. Yep.
Do you say hippos?
I did say hippos.
Where
yes.
Hippos here?
Oh, so that's another story. So yeah, no, they are not woolly hippos. So hippos have been around at several points in the past. The most common period when we find them is during the last interglacial, about 125,000 years ago, and they have had a Mediterranean distribution in the past, obviously present in Africa, but present in southern Europe for most of their past history, again, constrained by human activity. Just goes to show, like, the ones that have been released from in Colombia, how well they're doing when you move them to suitable environments. So 125,000 years ago, there were hippos all over Britain. They're present, that we've got sites in the southwest, and they go all the way up to the North Yorkshire Moors. The furthest north is Stockton-on-Tees. But we have recently been working on even older hippopotamus material from an extinct species, so not the one that we find in Africa today. And we've just published the oldest hippo fossil from the site of Westbury Sub-Mendip in Somerset, and it's about 1.2 million years old. And it dates to a warm period in the early Pleistocene, a really poorly known period. And these things were huge. They were bigger than the modern African hippo, slight differences in the skull. But it is special having hippos in Britain because they don't appear all that often. And the fact that the last interglacial, for example, was about 3 degrees warmer, it was enough to encourage them up from the Mediterranean into Britain. We know that winter temperatures must have been mild because hippos can't cope with seasonally frozen water bodies today. They certainly don't, they don't thrive in that type of environment. So warm summers, mild winters.
A bit warmer than...
So a bit warmer, yes. But by the same token, we had elephants and rhinos in every warm stage in the past. It was absolutely normal to have them in Britain. And had they not gone extinct at the end of the last ice age, probably because of those unusual climatic oscillations, we would still expect to have elephants and rhinos in Britain today. They should be living here today, yes. No, they're not the current species, they're extinct species. They went extinct at the end of the last ice age, but we'd had them in every warm stage in the past, going back 500,000 years. So. Oh, hold on. Oh, sorry, there is one more.
I was just going to say, can you read the chat function?
I can do. Shall we do one more in the room and then I'll pass to the chat?
Yeah, my geography is a little bit rusty. What route would they have taken to get to us? Because I was trying to remember, when was it that we had a sea all the way around this?
Okay.
I couldn't remember.
So prior to about 500,000 years ago, Britain was permanently connected by chalk land bridge to northern France. 450,000 years ago, we had the most severe ice age that we've ever had in Britain. The ice sheet reached as far south as North London. It's almost impossible for us to imagine that. And what that did was to block the southern part of the North Sea basin. All the rivers, the big rivers like the Thames and the Rhine and the Meuse, are discharging into the North Sea. They get blocked by the ice and create a huge ice-dammed lake. Again, the scale of it almost incomprehensible. And eventually, catastrophic overspill from that ice-dammed lake blasts a path through the chalk ridge and then opens up the channel for the first time. So after 450,000 years ago, every time we go into a warm stage, an interglacial, water is released back into the oceans and Britain becomes an island. When we're in a cold climate period, water is drawn up to build the ice sheets on land. Sea level falls globally by about 120, 130 metres. So during the cold period, Britain becomes a peninsula of northwest Europe again. So there's a window of opportunity for species to get in and out before the sea level rises and cuts us off. And it's one of the reasons why actually studying the fauna in Britain has been so interesting, because there's that element of chance about what will get in or not. So yeah, it's a really good question, and it brings together this sort of, you know, the idea about the changing geography as well. So great, right, I'm going to pass to the chat. So let's put them in there. Okay, so there is a question from David Hall. Is there any data for insects, spores or pollen? Again, that is a cracking question, because in most caves it's too calcareous for there to be preservation of biological proxies such as insects, spores or pollen. And that's simply because these types of proxies normally survive better in more acidic conditions. However, for the most part in our cave, we don't have any of that. But at the level where the hyenas are, there are some really clay-rich deposits that seem to have been sort of infilling pools in the bottom of the cave. So some element of water perhaps trickling down. And from there, we have pollen and we have plant macrofossils. So things like fruits, seeds, nuts, that kind of thing. And we have evidence for open grassland environments, but also things like juniper, pine, there's a bit of tree birch in there as well. So so we do have a little bit of paleobotanical evidence. We are going to be looking for insects. We haven't found anything yet. So we have a profusion of vertebrates and also snails, which I haven't talked about as well, but also calcareous. But yes, unusual circumstances, but yes, we do have evidence for plant remains. Okay, right, is that the last one? Let's just have a look. Are there any good, right, there's another question. Are there any other good dig sites in the area? There's nothing sort of large scale going on that I'm aware of. We are sort of doing smaller scale excavations at other sites, but who knows what is buried in Mendip. I mean, there may be other caves under the scree slopes of Eber Gorge, for example, and it may well be that as we go down we will find other entrances. But no, there's only a handful of sites that are going on at the moment. So yeah, that's about the size of it. You might have come across the site of Sherford near Plymouth that was reported in the news quite recently, and that's a big housing development. So a new town is being built, and a cave site was found there during the construction process, so it wouldn't have been found if the construction hadn't happened. And we've been able to do a targeted rescue excavation there. And that's another very interesting story. There's woolly rhino, woolly mammoth, reindeer in there, and it fits with the bottom part of the gully cave sequence that I've been talking about tonight. But you know, the importance of our sequence is the length of time that it covers. So it's acting as a sort of framework, a reference site for these other smaller sites to be fitted in. Okay. Oh, there's another question in the room. Yes.
Hello, Professor Schreve. I'm a bit worried about this woolly rhino. It's going the wrong way. If it went up to the north of Scotland, surely that was the coldest part. It should have been heading the other way down to the Mediterranean for a holiday.
Except for the fact that it's cold adapted. That's the thing. It's got a, you know, they're animals that are typical of cold, dry conditions. So that's what they thrive in. And they have this woolly coat, which we now know from finding remains of the hair. Because, of course, I only find bones. I don't find the soft parts like the horns or the hair or anything. You have to go to the Siberian permafrost for that. But, yeah, they have astonishing cold-adapted features. So we know that their hair had sort of hollow fibre, to help keep them warm. The coat's very complex as well, so it's got like a finer undercoat and a thicker over wool, if you like. So yeah, they were cold adapted, so they would have desperately tried to follow their preferred environment. But I think the thing that kills them off is not the cold, because it's the last glacial maximum that they're heading into. It's the fact that probably snow cover becomes too too significant for them. And remember, these are just like rhinos today in the sense that they are long-lived, slow to mature, have few offspring, it takes them some time to breed again. And so any kind of sort of disruption to their life cycle, and you can imagine that all these climatic changes would have broken up their ranges and isolated populations. We know from many species that they begin to lose genetic diversity thousands of years before they go extinct because of the ecological pressures that they're under. So rhinos, I think these rhinos are, they're already under pressure for thousands of years, and the environment begins to change in a way that doesn't suit them, and eventually they go extinct. But this is one of the reasons why we need to look at the species over different parts of its range to understand exactly what the final forcing factor was. There's another question in the chat. If hyenas were so adaptable, why the period when there were none on the Mendips? Okay, so hyenas were around during the last cold stage, during the last interglacial. They were around in previous interglacials. They eventually do go extinct by the last glacial maximum in Britain. So they're gone by 25,000 years. And that's because, as far as we can tell, and this is also drawing on evidence from modern hyena distribution today, they are the least tolerant of cold of all of the big carnivores. So they're pretty good in these open environments that we've described as of the Mammoth steppe. Summer temperatures about 13 degrees. It's pretty tolerable. They obviously wouldn't have, they probably moved away during the colder stadials, but they're surviving and thriving in these open, warm interstadials in the past. So eventually they go extinct in the last glacial maximum. We know that things like wolves, lions, and brown bears do survive, and these are all more generalist and more adaptable than hyenas. So a good question, but it's the last glacial maximum that eventually polishes them off. A comment, lovely, thank you very much. I'm glad you enjoyed it. Any remains of cats? I live in hope of finding a lion, maybe this coming year, but we do have remains of wildcat, and these date from the Holocene period, and we have a complete individual. I brought along a little jaw tonight. Actually, Penny, would you mind? I'll just hold it up to the camera, and hopefully people can see. It's that one. Yeah, it's that one. I should just. It's all right. It's quite robust. There we go. So I don't know if you can see this on the camera still, but that is a jaw of a little wildcat. So it's identical to the species that we find in Scotland today. And this is part of a complete individual. It's dated to about 10,000 years before present, and it's pretty much the youngest species that we have living in the cave. So, we have wildcat, and this is important, of course, for giving us more information about the fact that wildcats should be living down in southern England today and thriving very well in deciduous forest. It would be problematic to reintroduce them because of interbreeding and disease transmission with domestic cats. But where they are now, up in the Highlands of Scotland, is not the ideal place for them.
But Professor Schreve, I have a question, and can you give a range of timings to how long would it take a lemming or a vole or a shrew to travel from eastern Siberia to Britain?
Well, I think we're looking at several thousand years. They're not going to be moving quickly, but they expand their range more quickly than we realise. And obviously, they would have been a somewhat closer to us than they are today because they're restricted in their distribution today. So they're even further away now. But during a broad period of cold climate, even though, it's punctuated by these warmer episodes, they would have been somewhat closer to us, but it still requires a big movement in. But no, there I think we're looking at hundreds to thousands of years. I don't think anybody's ever tracked this kind of thing, and largely because we don't have the time depth to do it. But this is where the power of the fossil sequence comes in, because actually we can say, well, it appears at this point and it disappears. So presumably, if we've got a decent sample size, we can actually start to say something about when it was present or absent. Yes.
Has this excavation been public knowledge, or have you had big trouble keeping it secret?
So it is public knowledge. It is not yet properly published because of the sheer richness and volume of material that I'm having to get through, but we're almost at the point of getting together the first paper on it. When I first started, I was nervous about people finding the site, and in actual fact, particularly sort of the local community and caving community being very supportive and respectful of what we do. And we've got an excellent relationship with, for example, a lot of local societies like the Mendip Society. The only time we had a problem was during the pandemic, and we weren't able to dig that summer, and unfortunately the cave was broken into, and minimal damage because nobody would be able to, you wouldn't go in there and find bones of reindeer. It's just not like that, but annoying things were done, like pulling down my plumb bobs and things like that. And it was on the basis of that, I don't know if you noticed from the photos, but especially with the fly-through, there's actually a metal grille over that now. And it's been built in such a way that as we go down, we can add more onto it. So that's good. It can be locked and left, and touch wood, that's that will be fine. But it's in a part of the gorge where people are not supposed to walk, but of course people do, and many people are completely respectful and just enjoy sort of being there. I think they can see what goes on. They can see that there's some sort of excavation going on there. But yes, it's not a very well kept secret, perhaps. Yes.
How much worse would finding a relatively dry piece of open land that wasn't near a river be, and just digging down as you did there? You would absolutely have no chance of finding anything at all, no matter how far you dug, because plants have destroyed it all? Or is it just that?
No, I mean you can find all sorts of things. If you were to dig in a floodplain today or close to, you would probably find a series of water lane silts, and they could preserve material from the last few 100 to 1,000 years. Preservation is not the norm, though. I mean, the very fact that we're not, climbing through the streets of Bath, pushing our way through the bones of Ice Age mammals, means that most of them have disappeared for various reasons. They're either crunched up by hyenas, or all sorts of things could have happened to them. So, I mean, that's why caves are great places, because they're good repositories of material, and they're protected, and you can get material that's really quite old found in them. We do have open sites that are, there's spectacular Paleolithic archaeological sites that date to 500,000 years old. It just depends whether you have that perfect point where a site has been preserved, and then it's been found, often by quarrying or something like that. So, but yeah, you can learn a lot by digging metre by metre test pits in all sorts of places. You can build up a fantastic sort of local knowledge. It may not go back very far in time, but I think they do this in Westbury Village, actually, on the Mendips. They've had a programme of lots of people doing that kind of thing, so you can find out an enormous amount. But no, if you would have to know that there had been ancient river deposits there or something. You're not going to find anything if you just go randomly digging, or you'd be very lucky to find something. But a cave is a great place to start. Yes.
So, I mean, your work is really, really interesting, and fantastic presentation and everything. I was just interested to know whether you could apply any of your findings to the present changes in the climate.
I think mine is very much a story about responses. So the thing is that the climatic records that I've shown are drawn, they're drawn up by paleoclimatologists. That's their thing. So whether you're looking at records from the deep ocean or the highly detailed records you get from the Greenland ice cap, I mean, there you've got annual resolution going back 125,000 years. It's absolutely astonishing. But the question is, that's what's going on in Greenland. What happens to us? What is life like on the ground? How do we experience those changes in Britain? I mean, we're certainly, obviously, because our position close to the North Atlantic means that we are subject to we're very sensitive to these changes. So it's finding these proxy records that I'm interested in the responses to that. So I think the thing is, while I'm not creating climate records directly, I am using them to see how they affect species. I suppose for my other work, which has been looking at older interglacials, these warm stages, I've become very interested about how different they are. So interglacials that, some are very short, about 6,000 years, some of them are about 20,000 years. Some of them are warmer than the present day, some of them are similar to the present day, some of them are even cooler. So actually looking at those interglacials with which each have a different set of boundary conditions, that I think gives us a really valuable insight into, perhaps what a warmer world might be like. So.
Professor Schreve, I've got a question you may be able to answer. Obviously, since the Enlightenment in Western Europe, we've had improvements in mining and quarrying technology and so on. We have, paleontology and archaeology in a systematic way. But do you know of earlier peoples who were interested or had a speculative guesswork about objects of curiosity that they found?
I suspect strongly that kind of curiosity has been around a long time. So, for example, there are flint hand axes made 300, 400,000 years ago that there's a particular example I'm thinking of from Norfolk that is flaked around a fossil sea urchin. So someone saw that, thought, that's an unusual thing. I'm going to make it into my hand axe. And obviously in antiquity, people have been finding things and interpreting them in certain ways, but often in sort of, in ways that we would describe as mythology now. So for example, in the Mediterranean, there were skulls found that looked a bit bigger than a human skull, with seemingly a great big eye socket in the front, which were interpreted as the remains of Cyclops. We now know that those are dwarf elephants. They are hundreds of thousands of years old. This is another fantastic tale where very large animals get onto islands, they become isolated. Britain's too big for this, but an island, like Sicily or Cyprus or Malta, you get full-size straight-tusked elephants dwarfing down to the males are 1 meter high at the shoulder, and it's their skulls. And because elephants they've got a hollowed out part in the forehead, which is actually just a way of making their skull a bit lighter. Their orbits are on the sides. But of course, people would find those in antiquity and interpret them as cyclops. There's been all sorts of things like that, cave bear teeth were interpreted as, remains of dragons, all sorts of things like that. In fact, actually, one of the oldest records, in fact, probably the oldest record in Britain, comes from the late 1700s, and they're 3 teeth of a woolly rhino that were found at the site of Charton in Kent. And they are incredibly valuable because they were the oldest recognition of a fossil species. Now, they were reported on by someone who interpreted them as the remains of an extinct sea dragon. Now, he wasn't right. He was making the best guess that he could. We now know that they're woolly rhino teeth. But it was an initial appreciation that this was something that they hadn't seen. And in many ways, it was more enlightening at that time. At least they were thinking more widely, rather than interpreting everything as the remains of the biblical flood, because obviously early antiquarians struggled mightily with finding remains of extinct animals in context, sometimes with evidence for early humans as well. So yes, there's been a lot of water under the bridge since. But yes, I think people have often, in the past, they've speculated about what these remains might be.
Well, unless you'd like to have the last word, I think that we I really need to thank Professor Schreve for a fascinating lecture and ranging very widely, not wildly, very widely, very widely over long time periods, some beautiful graphics up on the screen, fabulous photographs, and such an engaged, open, willing way of speaking to us and answering our many questions. So thank you very much, Professor Schreve.